This video lecture deals with circular motion. The particular kind of circular motion that we will restrict our attention to is called uniform circular motion. The word uniform doesn't appear on the board, but what it means is that the speed of the object that's moving in a circular path doesn't change. The only thing that changes is the direction of motion of the object. I show a circular path whose radius is r. The center of the circle is there. And I show the location of an object moving in a circular path, 4 different locations. The speed of the object is described as being tangential because the velocity vector, whose associated speed is v, is tangent always to the circle. Because the velocity is changing, even though the speed is not changing, there is an acceleration. And without proof, I state that that acceleration always points toward the center of the circle. Circle center is there. So if the object is there at some moment in time, it's accelerating toward that center. When the object is up here, it's accelerating also toward the center, and so on and so on. Now, this should be a little confusing to most students. How can an object be accelerating toward a particular point without it getting closer to that point as time goes by? Well, don't worry about that. Just know the following, that there is an acceleration, but it's of the nature associated with a change in direction, not an increase in speed. And so I described this acceleration, symbolize it as A. Wherever the object is, its acceleration is symbolized as A, and its associated vector points to the center of the circle. Now, the question that I'll ask and then answer is this: how does one calculate that number, that acceleration number? What is the value of the acceleration? Well, without proof, I declare that it's given by this equation: the square of the speed divided by the radius of the circular path. Now, because this acceleration vector always points toward the center of the circle, and that's because there's a central attracting force at that location, maybe the pull by the sun on a planet that's orbiting in a circular path, or the pull by the proton in a hydrogen nucleus pulling on an orbiting electron. Because it's a centrally attracting force and a centrally looking, we can say, acceleration, the name we give to this acceleration is centripetal acceleration. I may write down that word later, but for now it's centripetal. Tripetal. It's not centrifugal, which is a force that you've been made acquainted with in your studies of chemistry. There's such a thing as a centrifuge. But this is a centripetal force, or rather a centripetal acceleration we're talking about here. Let's work a couple of practice problems involving this equation. First example, we have an object moving in a circular path whose radius is 1.6 meters. Its tangential speed is 4 meters per second. And then we calculate its centripetal acceleration. Squaring the speed divided by the radius, the numbers work out to exactly 10 meters per second per second. You can check to see the units work out. That m gets squared, the s gets squared, but that one of the m's on the m squared there is canceled by that m, so you're left with just 1m slash s squared. Pretty exciting work. Now let's look at the final example. We have an object moving in a circular path of radius 3/10 of a meter. and it's executing 40 revolutions per minute, 40 RPM, revolutions per minute. In order to calculate the centripetal acceleration, using this equation, we need the R, and we have it already, it's on the board. And we need the speed V. So let's calculate the speed first. The speed of our object can be found by dividing the distance it travels by the number of seconds it takes to travel that distance. Well, the numerator of this ratio is 40 times the circumference of the circle, which is 2 pi times the radius. 2 pi r is the circumference of a circle. 40 of those circumferences is the distance, total distance the object travels in 60 seconds, 1 minute. The result is that number, 1.26 meters per second. We square it, leaving the units off until the end. Divide by 0.3 meters, final result, 5.29 meters per second squared. You might want to compare that acceleration with the acceleration an object has that is undergoing free fall, 9.8 meters per second. Well, in our next lecture, which will be an introduction, just as this one is, I'll discuss a thing called the radial line or the radial axis, which plays an important role in applying Newton's second law to objects undergoing circular motion. But that's all for now.